Welcome back to the Organic Chemistry playlist. In this episode, we will be looking at mono-halogenation. In the last episode, we looked at some general properties of radicals and what radicals actually are. This is the first reaction of radicals you'll see, turning useless alkyl groups into synthetically useful alkyl halides. So, right, in this episode, we'll just look at this mechanism here. There's three parts. There's initiation, propagation, and termination, as you'll see. Without further ado, let's get right into it. So, like I alluded to before, we can turn alkyl groups or alkanes into alkyl halides, right? And we'll get a racemic mix of the two. Granted, monohalogenation does occur. Note that this could happen many times. You could get polyhalogenation, right? So it's quite simple. You just use a halogen gas. Now we see this with chlorine and bromine. Fluorine's possible, but there's two things about that. One, fluorine isn't a good leaving group, so it's not very synthetically useful, but sometimes you gotta fluorinate things. And another reason you don't do fluorinations is they're quite violent reactions, and the enthalpy of fluorine is about twice that of chlorine, and chlorine's a very exothermic process when it does monohalogenation itself. So fluorine being twice that, it's kind of a violent reaction. Iodine isn't thermodynamically favored at most conditions we can give it. It is still possible, but just not something that's practical when you could just add bromine, which is almost as good as a leaving group as iodine is. Okay, so quite simple here. We're going to have our first step, which is called initiation. Initiation of a radical mechanism is when you have a non-radical species being turned radical. So what does that look like? Well, if we have a non-radical species like bromine gas and we subject it to photochemical conditions, we're going to see homolytic bond cleavage of that bond where two bromine atoms respectively get their own electron. So our product will be two bromine radicals. That's all you need to know for the initiation step of monohalogenation. It's the same with chlorine and fluorine. So quite simple here. Now propagation. Propagation is when you have a non-radical species react with a radical species and you get a radical product and a non-radical product. It's kind of hard to see. Just I'll put it on the board and then you'll be able to see it a little better. So let's take our non-radical species, our alkane. So we have an alkane here, and we have a nice juicy hydrogen. All right, so and then we have a bromine radical, let's just say. So I have a bromine radical and our alkane. Well, we're gonna see something that's called hydrogen abstraction. That bromine radical is gonna steal that hydrogen to make hydrobromic acid. So hopefully you can see the arrows here, a coupling of an electron from this sigma bond to the carbon and the radical bromine there. And then we're gonna dump a radical electron onto our alkane. So we get a radical alkane, but notice that now our bromine radical was used up and is now HBr, hydrobromic acid. Quite simple, isn't it? Another propagation step, because there's many of these propagation steps occurring at once, is okay, what will this radical do? Well, if our product is to get this, maybe it could come back to a non-radical species of bromine gas, abstract a bromine, and reform our radical. So this is kind of just a cyclic process, right? So now we have, and what I like to do, which helps out, is for propagation steps, put your non-radical species as the reactant. And then on the arrow, put the radical species that's reacting. So in this case, we have our radical alkane. And it's gonna come over here and couple with a bromine and make another bromine radical. So what do we notice? Well, we've made our product here, right? And this would be racemic because remember, the shallow pyramidal interconversion makes it so that radical can either exist on the wedge or the dash, basically, and that means that this will be racemic, but we are avoiding stereochemistry just for simplicity. So initiation, we made 2 bromine radicals. Propagation, we're taking non-radical species, reacting them with radical species, and they kind of swap, right? The radical species becomes non-radical, but the non-radical species becomes radical. And you can see that here. The alkane becomes radical, and then the radical alkane in the next propagation step neutralizes itself and reforms this. Notice how we have a bromine radical here, which can come back and do this step here. So it's kind of a cyclic process, although it's not catalytic. It's just kind of cyclic in its nature. So those are the 2 propagation steps. All reactions must come to an end unless you're like a catalyst. So some termination steps is when 2 radicals eliminate each other. Quite simple. Hopefully that makes intuitive sense. Initiation, we make radicals from non-radical species. Radical plus non-radical in propagation. Now it's radical plus radical. There's many radical terminations. For example, 2 bromine radicals can come together to reform bromine gas. That would be the elimination of 2 radicals. What we care about more, for example, would be, let's say we have one of our radical alkenes and it reacts with a radical bromine, right? What's our product going to be? Well, they couple together and eliminate each other. Well, we get that desired product once more. So we're not only making it in the propagation step, in making that cyclic nature of that bromine radical, but it also, in termination, is making our product. So that's important to point out. Another less likely termination step that you won't see in high yields is when the two alkyl groups destroy each other. And even if this was a problem, the nature of these molecules, let's say you did a column, you'd probably be able to get rid of them. So don't worry about stuff like that. So yeah, you just get coupling of these alkyl groups here. So that's mono-halogenation. Again, I just want to emphasize that this is very synthetically useful. If we can make an alkyl halide from something, all alkanes are good, they're shit. I mean, like what are you going to do with that? If I wanted to make, I don't know, this molecule here from this, and I said, okay, go for it. The only step you can do to actually get anywhere is to add an alkyl halide. And then you could do some sort of SN2 or E2 reaction. And then you could follow it up and do some other chemistry. And then you start getting more complex and complex molecules. That's why mono-halogenation is very important here. And just remember, there's 3 steps: initiation, propagation, termination. That's going to be all. I hope you enjoyed.